Alright, so this is the back page of the work and energy homework practice. These are a little unlike what test questions would be, but if you understand these, you're in really good shape. So this one talks about driver's ed books providing tables which relate a car's braking distance to the speed of the car. Use what you know about kinetic energy and work to complete the table. Assume a car's braking force is constant. So what I know about work and kinetic energy is, especially for braking, they are going to be equal. If you think about it, your car is traveling along with a certain V, meaning it has kinetic energy, and then it stops. V is equal to 0. That means KE is equal to 0. Where does all that energy go? It does not go into PE. It doesn't go up a hill. It doesn't hit a spring. It's the work done by your brakes. So the relationship between these two, force times distance equals 1/2 mv squared. That's your two equations. The braking distance is proportional to the velocity squared. The mass of the car doesn't change. That's a constant. And the force, it says, is constant. So basically you can say D is proportional to V squared. So that's all well and good, but we have all these open spaces here. We have to figure out what's the best ones to go at first. If you look at 20, that means you're halving your velocity. Because of the square term, that means your D is going to be quartered. So that's the first one I can do really quickly. A quarter of 20 is 50 feet. Once I have 20, I think the next one that's easy to do is the 60, because now my velocity is 3 times as much. So my distance, because of that square relationship, is going to be 9 times the distance. So 9 times 50 is 450 feet. Following the same idea, I can then do the 30 versus the 60, which is halving my velocity. So my distance would be 1/4, but it's 1/4 of this 450. So this would be 112.5, I think. And then the last one, there is no easy one. So if you compare 20 to 50, your V is 2.5 times. But remember, you have to square it, so it ends up being 6.25 the distance. I think that's what 2.5 squared is. So 6.25 times 50 is 312.5 feet. Again, I know this is not easy, but if you're getting better at understanding the relationships, you don't have to do as much math, which we all appreciate. All right, next question is a conservation of energy question. No friction, that's great. What that means is the KE and the PE, the sum of those two will always be constant, always be the same number. So the trick here is figure out what that is somewhere. I think the easiest spot is at the top here. The total is 450,000 joules. So that's our number that's always going to be constant. If we go in order here, A, they want the height. Height you get from mgh, if that's equal to 450,000. I believe the answer is about 46, maybe 45.9 meters. B is 0 because your kinetic energy is 0. Next question is C. What's the kinetic energy at C? At C here, what does it tell you? The PE is 200,000, so 200,000 plus the KE has to equal 450,000. So that's pretty easy. It's just 250,000 joules. They want to know the height at that point there, which means you have mgh, and they tell you that this is 200,000. You're just going to solve for h. You know the mass is 1,000 kilograms, so you can basically do the math on that. It's 20.4 meters. Again, just solving for h. The v at that point there, that e, you're going to set 1/2 mv squared equal to, I think we just found it was 250,000 joules. Back out what v is. I got 22.4 meters per second. By all means, double check my math. Down at the bottom here, the kinetic energy, Well, let's look at, if you're at a height of 0, that means your PE is 0, so G is 0. That means all of that 450,000 joules of energy is kinetic energy. And again, we can set that equal to 1/2 mv squared and solve for V. I got 30 meters per second. All right, moving on. What is wrong with the following graph, the relationship between PE and mass? Well, PE is equal to mgh. That's the only potential energy that involves mass. The other potential energy equation is 1/2 kx squared. That involves springs, which we don't worry about the mass. It's the spring constant. So the, I guess, answer A is it's not a square relationship. It's a linear relationship between PE and m. So it should look something like this. What relationship is the graph a better representation of? I would say a couple different ones. This one, if it was energy versus stretch, then it would be like that. So PE of a spring versus x would be fine. Or if it was kinetic energy versus velocity, that's where the exponential curve would come from. So either of those would be good answers. All right, last question. Graph the relationship between PE and mass and height, and the relationship between KE, mass, and velocity. PE, mgh. Between mass, it's linear, so it should be a straight line. Between height, it's linear, should be a straight line. KE, 1/2 mv squared. So KE and mass, linear. KE and velocity or speed, square relationship.